Have you ever wondered how you teach a computer to think? I mean, not just to crunch numbers, but to actually strategize, to find the smartest, fastest path through a whole maze of possibilities. Well, today we're going to dive into exactly that by looking at how a super simple kids puzzle became this foundational tool for teaching computers how to get smart.
So before we jump in, we got to get our heads around a key idea in AI research, the toy problem. Now, don't let the name fool you. These problems aren't used because they're trivial or easy. It's actually the opposite. They're used because they take a massive, complicated challenge, think logistics or pathfinding, and boil it down to a clean, simple form where we can test our ideas.
And here it is, one of the most classic toy problems ever, the 8 puzzle. On the left, you've got the initial state, a total jumble. On the right, the goal state, all neat and in order. The goal, super simple, just slide the tiles around to get from start to finish. Sounds easy for us, right? But for a computer? Well, that's a whole different story.
So how in the world do you teach a computer to solve this? Well, like any good student, the very first thing it needs to learn are the rules of the game. The rules are pretty straightforward. You can only slide a tile into the empty spot next to it. No jumping, no moving diagonally, just simple up, down, left, or right moves. But here's the catch. These simple rules create a surprisingly massive number of possible paths, and the computer has to somehow navigate through all of that to find the one right answer.
Okay, so let's get into it. The most basic, kind of gut instinct way for a computer to solve this is to just, well, try everything. This is what we call an uninformed or blind search. It literally has no strategy. It just plows ahead, checking every single possibility it can. One way to do this is called breadth first search, or BFS for short. Think of it like this. It explores every possible first move. Then it explores every possible second move that comes from those. It goes level by level. It's incredibly thorough, and it guarantees you'll find the shortest path, but you can imagine it takes a long time and a ton of memory. The other blind approach is depth first search, DFS. Now this one doesn't go wide, it goes deep. It picks one path and just follows it all the way down the rabbit hole as far as it can go. If it hits a dead end, it backs up and tries another path. It's a lot easier in the computer's memory, but man, it can get lost on some ridiculously long, inefficient path to nowhere.
So this leaves us with two pretty flawed strategies, right? BFS will find you the best solution, but it might crash your computer trying to remember everything. DFS is lighter on memory, but it might take you on a crazy scenic route to get there. The bottom line is both of these blind approaches are just incredibly slow. They burn through a staggering amount of processing power. And this inefficiency, that's the real problem we need to solve. It forces us to ask a much better question. How can we make the computer search smarter, not just harder? Answering that, well, that leads to a way more elegant way of thinking. This right here is the critical question. What if we could give the computer a sense of direction? You know, like a little whisper in its ear saying, hey, that move over there, that one looks a lot more promising. What if, instead of just wandering around in the dark, it could have a hunch? And that brings us to the big aha moment, the heuristic. It sounds like a complicated word, but a heuristic is really just a fancy term for an educated guess. It's a rule of thumb, a shortcut that estimates how close the puzzle is to being solved. It's basically like giving our blind algorithm a pair of glasses. So how do you actually quantify a hunch? Well, one simple way is to just count how many tiles are in the wrong spot. Easy enough. But a much smarter way is something called the Manhattan distance. It adds up the total number of squares, up, down, left, and right, that each tile has to move to get home. And this is a way better guess because it estimates the amount of work left to do, not just how many things are wrong. And this all leads us to the hero of our story, the A-star search algorithm. A-star is absolutely brilliant. At every single step, it combines two things. First, it looks at how many moves it's already made to get where it is. Then it adds its educated guess, the heuristic, of how many moves are probably left. By always picking the path with the lowest total score, it makes incredibly smart decisions. So, we have our blind brute force methods, and we have our new smart heuristic guided search. Let's see what happens when we put them head to head. And trust me, the difference is, well, it's nothing short of dramatic. I mean, it all comes down to this, right? Does adding a simple, educated guess really make that much of a difference? Just how powerful can one little hunch be?
Oh, yes, it's a huge deal. The data shows that, on average, a smart search needs only about 4.5% of the computing power that a blind search chews through. Let me say that again. That's a 95% improvement in efficiency. That is just staggering.
And this chart says it all. A note here is basically just one arrangement of the puzzle the computer has to consider. Now look at those huge, massive bars for the blind searches, BFS and DFS. They have to think about hundreds and hundreds of possibilities. Now look over to the right at the heuristic searches. Their bars are so tiny you can barely even see them. This isn't just an improvement, it is a total game changer.
The numbers themselves are just wild. Raised nodes is basically how much memory it takes, and explored nodes is the processing power. The uninformed searches are looking at hundreds of nodes. The informed search, it brings that number down to just a handful. It's literally the difference between searching an entire library for a book versus someone just telling you exactly which shelf it's on.
Okay, so this isn't just about winning a little sliding puzzle game. This core concept of using an intelligent guess to cut through massive complexity is at the very heart of technologies we rely on every single day. And that's exactly why the 8 puzzle is such a classic in AI. As this paper points out, it is the perfect stripped-down case to show the monumental power of searching with a hunch versus just searching blind. So, why does any of this matter to you? Well, that same A-star logic is what your GPS uses to find the fastest route and dodge traffic. It's what helps characters in video games hunt you down so effectively. It guides robots through warehouses and helps companies optimize their entire supply chains. It's everywhere. So ultimately, the big takeaway is this. Teaching a computer to have a hunch is what makes all this possible. That jump from a blind, brute force method to one guided by an educated guess, that's the difference between exhaustive labor and actual intelligence.
And this leaves us with a final, really cool thought. A simple children's puzzle helped us unlock a fundamental principle of artificial intelligence. It really makes you wonder, what other simple problems are hiding out there in plain sight, just waiting to teach us how to build the next generation of truly intelligent machines?